So are we good to get started then?
I think so.
All right. Excellent. So our presentation is on mechanical engineering, as you've probably, gathered. And so I guess we should introduce ourselves really quickly first. My name is Hannah. I'm in my last year of mechanical engineering. Yeah, I'm from Cole Harbour, which is, close to Halifax.
And I'm Jasmine Solsley. I am also in my engineering around Vancouver, BC.
And my name is Emma Fudge. I am also in my final year of engineering or mechanical engineering, so we're all in the same class, and I'm from New Brunswick.
Excellent. So we can get started. So I know we maybe don't have that much time, so maybe, but if you want to put in the chat kind of what you think about mechanical engineering, what you think that they do. Feel free to have a think about it. You can even just think to yourself if you don't want to say anything in the chat. I know it's kind of early, but we'll maybe just truck along. So obviously there's some views in the media of mechanical engineers. They tend to be a kind of certain type of person, normally a guy maybe, and you're working with cars and trains and stuff. But it's a little bit more, complicated than that. There's a lot of different aspects of mechanical engineering that are maybe less obvious if you're not in the field itself. And we're going to get into that a little bit today.
Perfect. So I'm just going to quickly talk about mechanical engineering design. This is something that we talk about quite a bit in mechanical engineering. So we think of design as a little bit of a cycle. So you might start at one spot in the circle and then move on to the other, but design is a continuous improvement process. So, you'll start by understanding the problem. So that's where this little empathize area comes from. So you're trying to understand a problem and trying to, solve a problem for another person, and then you want to define what that problem is and ideate a solution. And then when you come up with your solution, you're going to move on to prototyping, testing, and then implementing your device. And then once you've gone through this whole circle, you might come back and say, oh, this part of the design didn't work. And so you go again to defining the problem. So it kind of moves in a circle, which is a big part of what we do. And then quickly, this is a few of the fields that mechanical engineers work in. This is not even a fraction of the full list of where we work, but we'll go into a little bit more detail about each of these areas, starting off with Hannah.
Yeah, so the first one we're going to talk about is automotive. So this is cars and trains and all of that kind of stuff. Obviously, this is a pretty common thing in mechanical. I feel like, we see a lot of this, but there's a lot of different elements of it. Like, obviously, when we think of car engineer, sometimes we just think of, oh, that's just one job. But these are all different areas that people can have entire careers in, just kind of within the automotive industry itself. And same with aerospace. There's all sorts of different aspects to it. So this is to do with, planes, but we're also looking at like avionics, just stuff in the air, really, which is pretty cool. And a very important aspect of mechanical for sure. And then manufacturing. Manufacturing is all about making stuff. Almost everything has to be manufactured in some sort of way. And so mechanical engineers have a very big part in that. We look at how to do that, the best way to do that, how to do that quickly, how to do that, most efficiently, most effectively. And so that's a huge part. And just like with the other ones, like we have all of these little subsections that you can have like entire careers in, just within the manufacturing industry itself.
So another one is metallurgical. So metallurgical engineering, it's kind of everything to do with metals, how you can obtain them from the earth and how you can process them to give you the properties you want and to be able to use them in the ways that you want. So it combines physics and chemistry, and it has to do with things like mining, extraction, treatments, alloys, which are mixtures of metals, and then how these metals and alloys will respond to changes in their environment. So if you're going to work in this area, you could be doing something like really hands-on, like working at a mine, or you could be doing processing, designing processes to work with the metals, and lots of things in between. Next one, please. And then biomedical, which some people might be familiar with. It's really everything to do with the medical field and designing either devices or processes, designing or installing them to help medical professionals either diagnose or treat conditions. So it can be artificial internal organs or replacements for body parts like prosthetic limbs, or machines for diagnosing medical problems like the MRI that you see in one of the photos below. So this combines biology, life sciences, medicine, and clinical applications with engineering design to allow us to make advances in how we improve human health. So like, for example, this one on the left-hand side here is a device for levels. So instead of having to prick your finger all the time, you have this thing that's continually in your arm and you can use an app on your phone. And then mechatronics and robotics. So these two are kind of related. Robotics is just a subset of mechatronics. So everything to do with robots, programming, automation. So this can be done in manufacturing. So you could have like a robotic arm doing part of your manufacturing process, or like in this photo, you can have like everything up to a large scale, whole human-sized robot, which you might have seen about. There's some pretty popular ones online. But yeah, so this one's a pretty cool field that's up and coming and becoming a lot more popular. So robotics can be used like everywhere from ocean technology to biomedical applications, manufacturing, like I mentioned, and really just about anywhere. And we're going to be seeing those being used in a lot more places as the years go by. And then the last one that I'm going to mention is thermodynamics. So this is an area that we take a lot of courses in, and it mostly just deals with heat and energy and the transfer of heat and energy and how you can sort of manipulate those to achieve things that you want. So some of these pictures below, you might recognize the one on the right. That's the power plant in Dartmouth. So some of the major applications of thermodynamics are in power plants and power generation, boilers, and then the engine of your car, air conditioning in your house, and everything like that deals with thermodynamics. So it's a field that really touches just about everything. Can't hear you, Jasmine.
Oh, sorry, I was muted there. So we're going to move on to the next section, which is CAD/modeling/FEM. If you don't know what these acronyms mean, so CAD stands for computer-aided design, and then FEM stands for finite element method. So this is essentially a field where you're taking in the help of computers to model your designs or model a problem. As you can see on the bottom there, I'm sure you've seen this meme before, but it's the thermodynamics of a lobster. So that's kind of the things you can do in this field, is you can take something kind of, take pretty much anything and model it up and then see how it'll behave in your model and then compare it to real life. So modeling really helps us bring down the cost of producing items. So, as computers have gotten better, we've moved from designing our things on pen and paper to using 3D models. So some of the benefits of using a computer for design, for one, it lets you visualize your models and see the design, and doing that, you can make changes quicker than if you were to use a pen and paper. It also lets you see a lot more detail. So the models you create will look very realistic and similar to what your designs might look like in real life. Next, this is a pretty big one, is optimization. So it's a lot cheaper to find issues in your design when it's on a computer screen than building, for example, building an entire car and then realizing, oh no, the tires actually don't fit, or something like that. So this is a great part of modeling and CAD. Next is specialization. So there's a different type of CAD or modeling software, finite element software for pretty much any application. So in that bottom example, you're looking at, you're basically putting a model into a wind tunnel and seeing what the aerodynamics are. And then that top model is just a car, so that's to actually build the parts, and then from the parts you can build the actual car itself. And then lastly is realization. So when you take a look, so it's easier to bring your design into real life from your model versus starting from scratch with absolutely nothing. And I haven't really touched a lot on FEM, but FEM is basically analyzing the different stresses and strains and how your design might fail using a computer. Perfect. And then moving on to nanotechnology. So this is it's also an up and coming field in mechanical engineering. You might have heard of it before, but it's basically dealing with a scale that is 100,000 times smaller than your strand of hair on your head. So it's basically looking into how we can make the, micro nano robots, nanotechnology. So a big part of nanotechnology is in biomedical. So there's a lot of design happening in nanorobots to deliver kind of personalized medicine. But it's not just in biomedical, it's not just robots. You can also take a look at materials and such as a big part of nanotechnology as well. And I think this is a very interesting and up and coming part of mechanical engineering. And moving on, we have consulting. So a consultant is basically just a kind of a go-to person for advice and expertise. So as a consultant, you kind of become the master of all knowledge, mechanical engineering. And so what they'll do is they will provide advice and expertise to other individuals or organizations. And this is going to be to help improve them in their business performance or in terms of their operations, profitability management, organizational structure, as well as business strategy. So as a mechanical engineering consultant, there's a few things that you might do, which might involve evaluating design sketches, comparing test results, preparing drawings of parts, reviewing project blueprints or instructions, conducting tests, as well as coming up with labor cost estimates, determining plant space, and recommending equipment life. All right, next we have HVAC, structural or building system design. So HVAC stands for heating, ventilation, and air conditioning. So again, this is similar to the thermodynamic slide that Emma talked about. So you're basically trying to make a space comfortable. So if you're in a room right now, there's probably some sort of HVAC system installed. And so a few of the areas covered by HVAC engineers would be the maintenance, installation, inspection, and then servicing of HVAC devices. And again, so this all ties into the structural design of a building. So every building is going to need an HVAC system. And so we're the ones that deal with all of that when it comes to a giant construction project. And then next up, we have materials. So in materials engineering, you're basically just interested in how a material is going to react when you put it in a specific situation. So some examples of where you might need a materials engineer or need to have some knowledge on materials engineering would be in aerospace or automotive. So in aerospace, you'd probably be interested in looking at how hot the outside of a plane gets, because that might play into, if the plane gets too hot, it might stop working properly. And then in automotive, you want to take a look at something maybe like crumple zones. So in that top right picture you see there, so you would much rather have the front of your car crumple and compress rather than shatter into a million pieces. So that's something that you would do in a materials field of mechanical engineering. And some other things you'll look at would be fracture and how things fail. You'd look at corrosion, you'd look at biomaterials. So again, that's similar to the biomedical. So everything kind of crosses over. And you might look at something like superconductors for electrical components. All right, moving on. So this is just a quick list of some of the areas that you might work in as a co-op student. So I'll let you quickly take a look at this slide, but we kind of touched on a few of them. And then in the next slide, you'll see a giant list of just a few of the places that we, or the students at Dalhousie have worked on or can work at. So if you see any of these logos that interest you, we've definitely worked in these fields before.
And this is just a list of a portion of the courses that we take. So we take a bunch of core courses with everyone else, and then in our mechanical class, and then you can take technical electives in your final year. So whatever areas you're most interested in, you can take more courses on those, and things like aerospace, nuclear, project management, robotics, and renewable energy. And then you can also do co-op, and we do a lot of different design project stuff through all of our classes and labs.
Really quickly, I think we have to wrap up shortly, but we are just going to quickly look at kind of different experiments and hands-on stuff that we get to do. Engineering is really cool because we have a lot of hands-on elements. So we get to like play with Lego, you know, do lots of labs and heat transfer materials and stuff like that, design projects, modeling labs, that kind of thing. And really quickly, we have some workshops. This is me and one of my friends and another girl in mech. We were doing a woodworking wood shop, and so we built this little shoe racky thing. This is a video, I'll take a little play, of a little robot we were using for a design for, I think, this event last year. You can see it doesn't always go to plan, but that's okay. And then, sorry, one second. And then this is just a really quick example of like what Jasmine was talking about with like the ideation and design process. So for a little design project I had last year, this is like CAD modeled. So I used a computer to model the leg mechanism that I wanted to use, and then we built it. And it's pretty cool to see how you can kind of look at stuff in design and then have it happen in real life. That's one of my favorite things about mechanical, is that you kind of get that hands-on element. You get to plan something, do all the math, do all the numbers, do all the modeling, and then you see it happen in real life and it comes to fruition. And I think that's pretty cool. So really, really quick, this is an example of something that we do in some of our classes, our design classes. Our prof will say something like, where are Pentagon bolt heads used in real life? And then we have to kind of go and think about it over the next day and see if we can figure it out. And they're actually used, I'm actually not sure the name of this thing, but you've probably seen them in your yards or in sidewalks or anything like that. But the reason that they use Pentagon bolts here is because they're a very cheap kind of safety measure, because most people do not have tools to access to be able to open Pentagon bolts. But if you do have the tool, it's quite easy to do. And so it's just like a little bit of a very easy little deterrence thing there. I know, I think we have to move on probably, but does anyone have any questions? No, are we good?